Hi, welcome back. This is Ken and we're on lesson 6 of our course on mechanics. In this lesson, we're going to discuss about your work and kinetic energy. And these are our goals for this lesson. First, we're going to understand and calculate the work done by a force. Second, we're going to understand the meaning of kinetic energy. And you're going to learn how work changes the kinetic energy of a body and how to use this principle. And we're going to relate work and kinetic energy when the forces are not constant. And lastly, we are going to solve problems involving power. But before everything else, let us define work in terms of physics. We begin with our discussion on work. How do you define work? According to the Merriam-Webster dictionary, work is defined as to exert oneself physically or mentally, especially in sustained effort for a purpose or under compulsion or necessity. Work is also to carry on an operation or perform a job through, at, in, or along. And then it is also defined as to pay for or achieve with labor or service. Or in our everyday language, when we are going to talk about work, it means that something that we do. So like say for example, something we do for a living or something that we are doing now. So what are you working on? Okay, so it's something like that. Like say for example, learning physics is a hard work. Okay, but in terms of physics, this is not our definition of work. And in the next slides, we're going to slowly um, get the definition of work in terms of physics. So to understand what work means to a physicist, consider the following situations. Okay, so on figure A, you have here a girl that is pushing a cart, and then the cart is full of loads. So as you can see there are many boxes on the cart. But while the girl is pushing the cart to the right, there is a stone that blocks the way of the wheels of the cart. Okay. Now since the cart is heavy and there's the stone, the cart does not move. And even though the girl already exerts too much effort, the cart is not moving. Okay. And in the second situation, or in the second figure to the right, you have here a man still pushing a cart. The cart does not contain anything, and uh, the cart is moving along a smooth road or smooth path compared to the path that is uh, traversed by the cart of the girl to the left. Okay, so in these two situations, who do you think does more work? Do you think it's the girl or do you think it's the boy? Okay. Well, um, if you're going to put work in the definition of in our everyday definition, you might say that of the two situations, it is the girl who does more work. You can also see in the drawing that um, the girl is already perspiring in pushing the cart, even though the cart does not move. And the cart is also heavy, so you can say that the girl applies more work or does more work. Well, as you can see, if you're going to compare it with the boy on the right, it seems that his life is easy, right? Now, let's see later who between these two does more work. Is it the girl or is it the boy? So in physics, work is done whenever force produces motion. Okay. So again, work is done whenever force produces motion. So there is one um, there is one condition for work to be done, and that is it should produce your motion. There should be a motion of a motion that is a result of applying some force to a certain body. And for work to be done, three conditions must be met. Using these three conditions here, we're going to see later which of the which between the girl and the boy is really doing the work. So the first condition is that there must be a force acting on the object. Okay, if you're going to compare your girl and then your boy, both the girl and the boy applies force. So this is checked for both situations. There must be a force acting on the object, and the object that we are talking about is the cart. Next, the object has to move a certain distance or displacement. So if you're going to talk about the cart should move some distance or some displacement as you apply the force. So if you're going to see here from condition number 2, the cart that the girl is pushing does not move, so that means work is not done on the first situation. And then third, there must be a component of the force in the direction of the motion. So again, there must be a component of force in the direction of the motion. And we're going to explain condition 3 later. We're going to dig into condition 3 deeper later. But again, these are the three conditions that must be met. First, there must be a force acting on the object. The object has to move a certain distance or displacement, and there must be a component of the force in the direction of the motion. So thus, in the previous situations, okay, the girl does no work. So there is zero work for the girl since the cart is not moving. Even if the girl is already perspiring a lot and is already tired pushing that heavy cart and trying to push it, even if there is a stone that blocks the motion, the girl does no work. Okay, so there is zero work in there in that situation. Now let's have here another example. Which of the following examples does work? The first is you have a mother lifting a baby from the crib. So you have here the force of the mother. The object first, the object that we're talking about here is this baby, and then our first condition is that there must be a force acting on the object. So for this case here, the mother is lifting the baby from the crib, so there's a force F that is upward lifting. And then in the second situation, a father carrying the baby across the room. So as the father carries the baby, the father exerts a force that is upward. Okay. And then our second condition is that the object has to move a certain distance or displacement. So let's try to see. So the baby, it moves from this part of the crib, and then as the mother carries it, it moves upward. So there is a displacement for the baby in the first situation. In the second situation, the father carrying the baby across the room. So as the father moves from, let's say from this point here up to this point here, so the baby moves from here to here. So there is this displacement D. So from the first two conditions, the first or both of these equations satisfies our first two conditions. So you might be tempted to say that both the mother and then the father does work. But do not forget that we still have our third condition, and that is there must be a component of the force in the direction of the displacement. So the force component should have a direction that is parallel or in the same direction or in the same axis as your displacement. So let's analyze situation A. the force of the mother is upward, the displacement of the baby is upward. So for this case, for the first example, or for situation A, the mother does work. But in the second situation, as you can see, the force of the father is upward, but the displacement of the baby is to the right. Okay, so as you can see, these are at 90 degrees, and there is no component of this force which is parallel to your displacement, so there is no Fx here. Fx is not available, the x component of the force, since the displacement is along the x-axis, so it does not exist. So for situation B, no work is done. Okay, so in identifying situations, in identifying which of the situation does work or do work, you need to satisfy the three equation or the three conditions. It's not only the first and then the second. It should satisfy the three conditions. The three conditions must be met in order for us to say that there is work done on your object or in your system. Okay, so we now define work as a force on a body does work if the body undergoes a displacement. But again, of course, the force should have a component parallel or in the same direction as your displacement. So if a body moves through a displacement S while a constant force F acts on it in the same direction, like say for example here, the box is initially located at this point, and then there's a force here, which you can say as maybe you're pulling the box or you're pushing the box, and then it moves some displacement S. Now, if the body moves through a displacement S while a constant force F acts in the same direction, you have your force and then your displacement S in the same direction. The work done by the force in the body is just simply your work is equal to Fs. Okay, so for this case here, you have your work is equal to Fs. Again, this is only the case when your force and then your displacement S is in the same direction. Generally, the work done by a constant force acting at an angle phi, the displacement is this one here. Of course, it's not always true that the force that you apply is or the displacement of the body is in the same direction as the force that you apply. Like say for example here, the man is actually pulling this cart in this direction, or pulling the box in this direction. The force is applied here at some, let's say, some angle phi, but of course this box will not move there, right? Displacement is not along this direction. This box will move to the right. Okay, and you have experienced this one many times, I think. So it's not always that the force is in the same direction as your displacement S. But here, as you can see, we can satisfy your third condition. If you're going to get the component of this force here, you have this component here, okay, which is your Fx in the same direction as your displacement S. Okay, so the work done by a constant force acting at an angle phi, like say for example for this condition, so the displacement is equal to your work is equal to Fs cosine phi, or it depends on you. You can use your theta, your alpha, your beta, any angle that you want to name the angle between your force and then your displacement. So you have Fs cosine phi. And the SI unit for your work is you have your Newton/meter, that is equal to joules. Okay, in honor of James Prescott Joule, which is the man on our first slide. Okay, if you have seen the image of the man on the first slide, that is James Prescott Jones. Now, interestingly, if you're going to observe your work is equal to Fs cosine phi, this is actually familiar, right? Okay. If you're not familiar, now let's remember this one. You have two vectors, A, and then another vector B. Let's say you have your two vectors A and B. And then what happens if we dot your two vectors, or you get your dot product or your scalar product? So you have your A dot B. You know that this is equal to AB AB cosine theta. Okay, and this one, it looks like your work equation, right? Your force is a vector, your displacement is a vector, and then you have some cosine phi here. So that means generally your work done is equal to your F dot S. So it is actually a dot product of your force and then your displacement vectors. Okay. Now we have here three situations. So by the way, work can be positive, work can be negative, and then work can also be zero. Like say for example, the previous example wherein you have your father carrying the baby across the room, the work of the father is zero. And why is that so? So let's discuss your different types of work one by one. So let's have this first situation here. You have your box, okay? You have your box here, and then you apply some force that is directed to this one, okay, at some angle phi. Okay, some angle phi, and the box moves to the right with some displacement s. Okay, we can get the components of your force F. So you have this one here, this is your Fx, and then this one here, this is your Fy. Your Fx is parallel to your displacement s, and then your Fy is perpendicular. Now this one here perpendicular to your displacement s. Okay. Your force component parallel to your displacement is equal to F cosine phi, and then yeah, it's F cosine phi. And you have here some angle phi, of course. So your work here is equal to your F and then S, and then you have cosine phi. Now, what do you think of this work done here? Is the work here positive, negative, or zero? Okay. Now you know that for this part here you have cosine phi. Cosine phi is positive. Okay. Cosine phi is positive when you have your phi is equal to zero, but your phi should be less than 90 degrees. So it can be your cosine zero, that is 1. Okay, if you have cosine zero, that means your force and then your displacement is in the same direction. Your force and then your displacement at the same direction. You have here cosine zero, so that is equal to 1. So you have your maximum work done. So this here can be positive when your angle phi is equal to 0 but is less than 90 degrees. Okay. So for the first situation, let me erase this one. So for this one here, your work is positive. Okay, so your work is positive on the first situation. Now next here, we have still the same box, but while you are applying a force in this direction here, okay, your box moves towards this displacement, okay, and measured from this horizontal here, this is your angle phi, which is already greater than 90 degrees. Okay, now what do you think of this situation? You have an angle that is greater than 90 degrees. If your angle phi is greater, is greater than 90 degrees, and when it is less than 180 degrees, you can observe that your cosine phi will have a negative value. Okay, so if your angle is less than or greater than 90 but less than 180 degrees, your work done is negative. A classic example is, wait, let me erase this one. Okay, a classic example for a negative work is when you have your force and then your displacement at by the way, it's greater than 90 and less than or equal to 180 degrees. So it's not only less than 180 but less than or equal to 180 degrees. So let's say for example you have a force that you apply here and then your displacement is at there. So you have 180 degrees and cosine 180 degrees is equal to -1. So you have a negative work. So what situations do you think you have your negative work? So one thing is that if you're going to put down your baby, okay, you're carrying the baby and then you put down the baby downwards. So your force is still upward, okay, because you're still carrying the baby, but the displacement of the baby is just downwards. Okay, so that is a negative work. Your force is upward, but you move the baby downwards. Okay, because you're not pushing the baby. You're carrying it. So you're carrying it. Your force is upward, but the displacement is downward. So you have a negative work done for that one. Okay. So the second situation, work is negative. Okay. So we have here, work here is negative. And then lastly, the third situation, the force applied is upward for the box, but the displacement is to the right. The angle here is 90 degrees. What is cosine 90? So cosine 90 is equal to 0. So as you can see here, when the force and then your displacement are perpendicular to each other, there is no work done on your system. So here, work is 0. So no work done for the third situation. So again, work can either be positive, negative, and 0. It's positive when your angle phi is equal to 0, greater than or equal to 0, but less than 90 degrees. Work is negative when it's greater than 90 degrees, or less than or equal to 180 degrees, and work is 0 when your angle is at 90 degrees, or your work or your force and then your displacement are perpendicular to each other. Let's have an example. So a man cleaning a floor pulls a vacuum cleaner with a force of magnitude 50 newtons at an angle of 30 degrees with the horizontal. Calculate the work done by the force on the vacuum cleaner as the cleaner is displaced 3 meters to the right. Okay. So again, a man cleaning a floor pulls a vacuum cleaner with a force of magnitude 50 newtons at an angle of 30 degrees with the horizontal. Calculate the work done by the force on the vacuum cleaner as the cleaner is displaced 3 meters to the right. So let's figure out the problem. You have a man applying a force magnitude of 50 newtons at an angle of 30 degrees. So your force here is at an angle of phi that is equal to 30 degrees. And then the vacuum cleaner is displaced to the right. So you have your displacement here, S, okay, which is equal to 3 meters. Okay, so here your work is simply your Fs cosine phi. So you have your work is equal to, you have 50 newtons, 50.0 newtons times 3.0 meters times cosine 30 degrees. By the way, the angle phi is always the angle that is the lesser angle, because if you can remember, you have two angles here. You have this angle here and you also have this angle here, but we're always referring to the smaller angle. So we have cosine 30, and your work done here is equal to 130 joules. So it's straightforward. Okay. So let's have another example. So you have here a particle moving in the xy plane undergoes displacement given by your delta S is equal to 2I hat plus 3J hat meters as a constant force delta F that is equal to 5I hat plus 2J hat Newton acts on the particle. So you're given with your two vectors, delta S and then your delta F. So you're asked to calculate the magnitude of the force and the displacement of the particle. That is on the first problem. You're asked of the magnitude of your vector F, and then the magnitude of your vector S. And you already know this one, so I'm going to leave this to you. But it's just again the square root of your fx squared plus your fy squared. So here you have your sx squared plus your sy squared. And solving this one, you can actually get some values of around here for your delta f. This is around square root of 29, and then for your magnitude of your vector s, this is square root of 13. So this is for 8. I'm not going to dig in deeper to this one. This is already, or you already know this one. But let's go to your problem B. Calculate the work done F by the particle. So your work done is just the dot product of your F and then your S. So here you have your 5I hat plus 2 J hat newtons dot with you have your 2I hat plus 3 J hat meters. So you already know your dot product. You just multiply the same components and then you add. So you have 5 newtons and then times 2 meters plus you have 2 newtons times 3 meters. Okay, so your work done for this case is equal to 16 joules. Okay, it's 16 joules. You can actually also use this one here. Use this values, but you need to find first your phi. That is the angle between your F and then your S. And you can find it later if you like. Okay, I'm going to leave it to you as an assignment. Now let's go to this situation. We have work and energy with varying forces. Of course, when you're trying to push a table, you're not actually always applying the same constant force. Let's say you started pushing the table with a force of 5 newtons, and then later you push much harder, so you apply 10 newtons, and then at later time you get tired, so you just push now with some 7 newtons of force. Okay, so you don't actually always apply constant force. Like say for example, for this case here, for a particle moving from x1 to x2 in response to changing force, and let's say that the force applied to the system is like this. So you have an increasing force, and then it slowly decreases. Okay, here you have your F, and then uh, your X, or we can also say that here you have your displacement S. Okay, so your F versus S graph. Many forces, such as the force to stretch a spring, are not constant. So if you're trying to pull a spring, there are instances when you're going to pull much harder, okay, in order to stretch it more. So in the beginning, you only apply some small force, but then if you want to stretch it further, you're applying a greater force. If you're going to push the spring, to compress the spring, in the beginning, you only apply some small force, compress a little, but if you want to compress it to the maximum compression, you are now going to apply a stronger force. So the force that you're going to apply to spring is not constant. Okay. In the figure, now the question is, how are you going to find the work for this case here? Like say for example, for this kind of force, okay, you have this force curve. Okay, how are you going to find the work done here? Now from your calculus, okay, the work done is just actually um, the area under this curve here. Okay, so under this curve we have this area. Okay, so this area here, so you have this area, and that area there is actually now equal to your work done. How is that possible? Okay, so on the figure to the right, we have the same force curve, and then what we do is we take some area, we get some, or we divide your, sorry, we divide your area into rectangles. So like say for example here we have this one rectangle here of the same width, and let's say for example you have here this rectangle also here. Okay, so you already have something that is constant. Okay, now what is the area of a rectangle? The area of a rectangle is just equal to your length times your width. So for this rectangle here, the area is just equal to the force Fx, so the force here, and then this width here. Okay, so you have your delta x. Okay, so that is the area of the rectangle, and as you can see, this is just equal to your work done. But we have a lot of rectangles. Okay, so in here we have divided your area into many sets, or many sets of rectangle. So you know that in order to get the total area, you need to get the sum. Okay, so in the beginning, okay, let me erase this one. So in the beginning, you have your work Fx delta x for any of this rectangle. Okay, if you want this rectangle, okay, for example, if you want this rectangle here, you have your work is equal to Fx delta x. But we have many of these rectangles. So in order to get this total area that we wanted, you sum all your rectangles, right? So the work total is equal to the sum from xi to xf of your fx delta x. Okay, but if you're going to observe, we have these areas here. Okay, let's say for example, let me choose a different color. You actually have this some areas here that is not included, and you have some areas here that uh, is overestimated. So what you do is you make smaller, you make delta x very small. You have delta x, you make it approach to your zero, so that your rectangle is very small, so that we can avoid these blue areas here, because we do not. It seems here that we are underestimating or we're overestimating. Okay, so if you take that limit, okay, if you take the limit such that your delta x approaches to zero, to make your rectangles very small of this function, okay, fx delta x, okay, from your calculus, this limit here is just actually equal to the integral from xi to xf of your fx dx. This is your Riemann sum integral. So to get the area under this curve here, okay, to get this total area, you can integrate your function fx, okay, because as you well know in your calculus, this curve here, it is defined by the function fx, okay, and let's just integrate that function fx dx from xi to xf, and then you have your work done, because you have now your area under the curve. So your work done is equal to the integral of fx dx evaluated from xi to xf. So for this conditions, I request you to review your calculus in order to understand the derivation. So I'm leaving you this assignment for this video. So you have a particle that is subjected to a force Fx that varies with the position as shown in the figure. So find the work done by the force on the particle as it moves from x equals 0 to x equals 15. So just some hint. Okay, again, the area or the work done is equal to the area under the curve. So that means under this curve here, you have this area. Okay, you're going to find this area here for your work done. You might think this one is something like a trapezoid, or you can actually also divide this one into segments to find it easier. Like say for example, I can divide this one into this one here. Sorry, this one. Let me do it again. I can divide this area so that I have this one, this triangle here, your area 1, and then also divide this one. You have your area 2 and then your area 3, and then you just get the sum of these areas, and then you have your work done. Okay, so this is an assignment for you.